In this illustration, we'll analyze the power collection at focus of a convex lens. We are given that a parallel beam of light with the wavelength given and intensity given is incident normally on two circular apertures A and B of radii also given here, and a transparent film of thickness 2000 angstrom and refractive index 1.5 is placed in front of the aperture A. We are required to calculate the power reception by a detector D placed at focal spot of the lens, and we can assume 10% of the power from each aperture is transmitted through the lens. So in this situation, first we can calculate the power through apertures A and B are. We calculate the individual powers. Power through aperture A we can write as intensity of light multiplied by area of aperture A, that can be given as 10 by pi multiplied by pi, and the radius of aperture is 0.001 whole square. So here pi gets cancelled out. Numerically we are getting it 10 to power minus 5 watt. Similarly, we can calculate power through aperture B is intensity multiplied by aperture area B, which is again 10 by pi multiplied by pi 0.002 whole square, which gives us 4 into 10 to power minus 5 watt. And as we are already aware of, lens never introduces any path difference even if the light rays are bending. But the path difference which is already there before falling on the lens, the same path difference will continue till focus. So in this situation we can calculate, due to the film, path difference in path of light beams at detector is, this path difference we can write this T multiplied by mu minus 1. This we already studied in concept videos, that if T is the thickness of a film and mu is refractive index, then it introduces a path difference delta as T mu minus 1, using which we can calculate the phase difference in waves at D is, phase difference we can write 2 pi by lambda multiplied by path difference. So this is T mu minus 1. If we substitute the numerical values, here we can see this 2 pi divided by, for light of wavelength 6000 angstrom, we can put 6 into 10 to power minus 7 multiplied by thickness is 2000 angstrom, this 2 into 10 to power minus 7 multiplied by this mu minus 1 is 0.5, and numerically when we calculate it we are getting it pi by 3. So if phase difference pi by 3, we can calculate directly the resulting power at D, which is due to interference. This can be calculated as resulting power at detector is equals to, as only 10% of light power is passing through the lens, so we can write it as PA plus PB plus twice of root of PA PB cos phi. This is the relation I am using for the interference of coherent light beams, and rather than intensity I have taken powers because only area is common here, and we multiplied by 10 by 100 as only 10% of light is passing through it. When you substitute the value of PA, PB and phi over here, see the value of power reception at detector can be given as this 0.1 multiplied by this 10 to power minus 5 plus 2 into 10 to power minus 5, and this is 4 multiplied by 10 to power minus 5 plus this will be twice of root of P1, P2 is twice of 2 multiplied by 10 to the power minus 5, and cos pi by 3 is 1 by 2, and numerically when you solve it, this will give us 7 into 10 to the power minus 6 watt. That is the result of this problem.